At this point, you know almost all the theories that you need to understand and to carry any hypothesis testing. But I think we need a couple of practical examples. So in order to settle this down and in order to understand how you can use it on practice. So let's consider a couple of case studies. Example one. We have a company that produce tablets, iPads or Android tablets, and they claim that a new tablet can work more than 20 hours without recharging the battery, in average, of course, if you watch YouTube videos with 50% screen brightness, right? So this is a quality parameter of the tablet. This is a selling point. Last month, company received complaints from users that claimed that time actually was below 20 hours. So now we need to make an investigation. We need to find out if our tablets, let's imagine that we own the company, if our tablets correspond to what user complains about, or we can say that no, they are good enough, right? Well, first of all, we need to define the null hypothesis, right? In this case, our null hypothesis that the customers are true. Customers are always right. So therefore, we should take this complaint seriously. And our default assumption is that indeed our tablets do not last that much as we claim. So the average time for watching YouTube videos in our tablets does not exceed 20. So it's 20 or less. Okay, so we make this based on the customer evidence. In this case, the alternative hypothesis will support our initial assumption that our tablets last more than 20 hours. So this is the greater than 20. Greater, it's the right part. So therefore, it will be the right tail test. You remember the tail of the test, it depends on the direction that you use for alternative hypothesis, right? So this is our null and alternative hypothesis. So now we also know which tail to use. Okay. The next is to define significance level. So which significance level we should use? Well, let's recall that if your significance level is too large, for example, 5%, then you have a risk of rejecting the correct null hypothesis, right? In this case, the risk will be 0.05, or it means that in 5% cases you can reject it, right? But it means that if we reject the correct null hypothesis, and you remember our null hypothesis is customer rights, right? So the customer's right. And it means that it will give us more complaints and probably drop of sales because customers will be unsatisfied. So in this case, it's kind of a big risk. So I want to avoid it. But if we accept incorrect null hypothesis, then it means that we will probably need additional investigation. But we don't know about this accepting incorrect null hypothesis yet. We are going to discuss it at the end of the learning sequence. So in this case, rejection of null hypothesis, which is correct, is kind of risky. So therefore, I will use a reduced alpha. So I will use alpha of 0.01. So it means that I will have only 1% chance to make a wrong decision, right? Okay, this is fixed. Now we can define a sample size. Well, again, it depends on how many resources you have. In this case, I will just use the fixed sample size equal to 10. So it means that I will take 10 randomly picked tablets from several, for example, production parts. And then I will investigate, I will test them, or actually my workers will test them. And then that will be the sample. So the sample size is 10. So you can see that I defined all these things before I actually carried out the experiments. That's very important, especially that you define alpha before you carried out all the experiments. So this is the result of my experiments. How many hours for the first tablet? So they watched almost 20 hours, a little bit less. More than 20, more than 20, more than 20, less, more, less. So let me just do it like this. So in 3 out of 10 cases, we have less, but in the other cases, we have more. It looks like the results are okay. Now, these are statistics. So strictly speaking, of course, I should make a plot and investigate it with the plots, and that's very important. But in this case, because we concentrate on tests, so let me skip the plotting part. So these are statistics. So this is the average time. It was more than 20 hours. So it's against the null hypothesis. It supports my expectations. This is the standard deviation and how big the variation of the time is. And this is the standard error. Right? So now what I can do, now I can make a test because I have everything for the test. So first I compute a t-score. You remember t-score, it's average of your sample, m, minus average of your population, mu, and divided to the standard error. So this is my t-score. And you can see the t-score is pretty large. It's 2.9. It's almost 3 standard errors away. So my sample average is almost 3 standard errors away from mu. On the other hand, you remember that extremeness of t-score depends on the sample size. For example, if your sample size is 3, then t-score of 4.3 is not very extreme, right? So it depends on many things. That's why we need to compute a p-value. In order to compute a p-value, let's imagine t-distribution. So this is our t-distribution for 9 degrees of freedom. And this is the t-score that we have. Because we use right tail test, the p-value will be this small area here. And since it's a right area, it's an area on the right, I need to take 1 minus CDF function for 2.9. That's my t-score. And this is my degrees of freedom. And that's the p-value. And that's the p-value. And now you can see the p-value is very small. It means it's kind of unlikely to get a sample with these statistics from this population. And if you compare your p-value, this is the p-value with your alpha, you can see that the p-value is below predefined alpha. So therefore, we have to reject null hypothesis. Since we need to make a decision, that's why I do this comparison. So in this case, we reject null hypothesis. So it looks like we don't have any evidence that supports this. Okay. Of course, you can do it much faster. In R, there is a special function. You already know it. It's a t-test. So if you combine all these time values together and run t-test, but in this case, you have to provide additional arguments. First of all, you provide the target value, this one, and you provide direction. But look, direction you provide, it's direction for alternative hypothesis. It's greater, right? So you provide the value and the direction of your hypothesis, and then you will get a lot of results. I removed some of the results. I just concentrate on the most important ones. You can see 2.9. It's almost exactly the one that we got. And this is the p-value. The p-value is actually even smaller. We got a little bit larger p-value because I rounded a lot of values down to decimals. So you can see that it still contradicts with our null hypothesis. So we have to reject null hypothesis at this significance level, right? So all in all, we can say that we have no statistical evidence that average time of watching YouTube videos in our new tablets is equal or below 20. So it looks like the average time is actually above 20. Look at this formulation. I didn't say anything specific. I didn't say that our time is not below 20. No, I say we have no statistical evidence. That's important because you still have a little chance, so that's exactly the chance, that in fact the null hypothesis should be accepted, right? The chance is small, and we have to make a decision, so that's why we compare it with this one, but it's still there. So therefore, my formulation is that no statistical evidence, okay? So that was example 1. Now let me show you another example, example number 2, where we have another story. Imagine that we want to, we have operators which look into microscopic images with some different cells and count how many cells they have in these microscopic images. We have a new operator, John, which will count this number. And we already have a very, very well experienced operator, Jill. We know that Jill works really, really well. So the count error is very small there. We would like to find out if John is systematically different from Jill. What it means? It means that if they count number of cells on the same images, the average number of cells should be the same, regardless if it's John or Jill. Okay. Of course, they will vary. Sometimes John will see a couple of cells more, sometimes a couple of cells less, but in average, these numbers should be the same. Okay. On one hand, it looks like it's not a case for one sample t-test because we have 2 samples here, but you will find out that actually it's not like this. We can still use one sample t-test. Well, first of all, we need to define null hypothesis, and that's how we can make it one sample t-test because they will work on the same images. So we will not have 2 independent samples. We will have one independent sample by taking a difference. So how many cells John sees and how many cells Jill sees on the same image, and then we take a difference. Okay. And if average count should be the same, then the average difference should be 0. So if average difference is 0, it means there is no systematic difference in counts. So it means that in average, the number of cells Jill and John finds in these images is the same. Now the alternative hypothesis will be there is a difference, right? So John, for example, counts more or counts less. It means that we need to use a two-tailed test. So we don't have any direction here. It means that we should use two-tailed test in this case. Okay. Now significance level. Well, again, if we reject the correct null hypothesis, it means that John will not be hired, although he is good enough. On the other hand, it's not a big risk because, I mean, we can find probably another operator, and John probably, if he is very well skilled, can find another job. So it's not a very high risk of doing something wrong. So in this case, I think using alpha of 0.05 will be a good idea. So in this case, I will use alpha of 0.05. Now, the sample size, again, I will skip how to define the sample size because we will have a dedicated video about how to define sample size correctly. So in this case, I will just use sample size of 10 because let's say we don't have more resources to test John and Jill for more than 10 images. Okay. Good. Then again, look, I defined everything before I ran the experiment. Now I ran the experiment. So this is the John's result on the same images, 10 images. And this is the Jill results on the same images, right? So you can see that sometimes John gives a little bit less, sometimes John gives a little bit more. You can see sometimes they agree on the number of cells, sometimes you have quite a big difference. So it varies, but we are interested in average difference. So in average, we would like to have 0. We would like that John and Jill in average counts the same amount of cells. So let's test it. Well, this is our sample. All these difference values. So I compute average. So this is average distance, and this is the standard deviation. And then I can compute standard error by taking standard deviation and divide to square root of 10. So this is my standard error. Now we can make a test, right? So the same idea. So first of all, we take m minus mu, and to remember the expected mu is 0. So in this case, this is m minus 1.2, and this is mu, the expected mu is 0, and divide to standard error. So again, we find a t-score, which is 1.41, which means that the average that we obtained in this experiment is by 1.4 standard errors smaller than the expected average, right? So again, we can make a t-distribution. This is t-distribution for 9 degrees of freedom. That's the t-score we obtained. And this is t-score, which gives you the equally likely, equally extreme sample, right? So it's as big deviation from the null hypothesis as we have, but on the other side. In this side, right? And then the two-tailed test, so therefore all these will be more extreme, all these will be more extreme, so we simply need to compute these two areas. And this is how to do it. We know how to compute the left area. It's the CDF function for the negative t-score, 9 degrees of freedom, so this is the area on the left. This is how to compute the right area, 1 minus CDF function for the positive t-score and 9 degrees of freedom, so this is the area on the right. Strictly speaking, I can compute only one area and double it because you remember t-distribution is perfectly symmetric, but I just computed it this way. So now we sum the areas up, and this is our p-value. So this is the chance to get a sample as extreme as we have, or more extreme, assuming that null hypothesis is true. Now we compare our calculated p-value with the null hypothesis, with the alpha, with the threshold, and then you can see that it's way above 0.05. So we accept null hypothesis here. So again, we don't have a statistical evidence for any systematic difference between operators. So in this case, we hire John because we don't see any systematic deviation from the Jill's results. Okay. In this example, because it's a two-tailed test, I can also compute confidence interval. I can compute if we, for example, John and Jill will work not on 10, but 10 million images, what should we expect as an average difference, right? So in this case, you remember we go the other way around. So we first define the probability. So this is the probability. This is the probability for the left tail. And now I compute t-score based on the probability, not based on the values, right? Now I compute the second t-score based on the probability, right? And now I can compute the interval. So I use the same expression, I use t-distribution, but now with t-scores that I derived from the probability, from the theoretical distribution. So this is sample, this is the t-score, this is the standard error. So this is the left boundary of the interval, and this is the right boundary of the interval. So this is the confidence interval. With 95% confidence, the true difference between John and Jill varies between -3 and 0.7, let's say 1, right? So it means that we can expect that in average, John counts by 3 cells less, or John counts by 1 cell more. We don't know where the truth is, somewhere in between. It can be that John underestimates number of cells, but it also can be that John overestimates number of cells. So because we don't see this difference, this clear difference, that's another way to support null hypothesis in this case, right? So the confidence interval doesn't cross 0, and therefore we don't see evidence, with 95% confidence at least, we don't see any evidence that there is a systematic difference between John and Gilbert. As usual, you can do it also in R. I just put all the counts into a vector, and then I run t-test for these counts. In this case, I don't provide anything because by default average is 0, and by default the direction is two-tailed, so I don't have any direction here. So that's why I didn't provide any additional arguments to t-test function. And this is what I get. Again, I cut some of the outcome just to fit it to the slide. So this is the p-value. This is the t-score. You can see that it's very similar to what we got by manual calculations. And this is the confidence interval. Again, very similar to what we got. So it also supports the null hypothesis. So now I hope you have a better understanding about the hypothesis testing and about t-test in particular, and also about how to use t-test for some practical applications. In the next video, we will try to extrapolate this knowledge for another test for variance of your sample.